Look around you. What do you see? Perhaps a book, a screen, or your own hand. All these things, and indeed everything in the cosmos, are made of atoms. These tiny particles are the building blocks of reality. They are constantly moving, interacting, and changing. This dance of atoms is what we call chemistry. It is a story of transformation. It is a story of creation. It is the story of chemical reactions. These reactions are happening everywhere, all the time, even inside you. Imagine atoms as tiny dancers on a vast cosmic stage. Sometimes they hold hands with one partner. Sometimes they switch partners. Sometimes a group comes together to form a new dance, and sometimes a group breaks apart. These changes in partnerships are chemical reactions. They are fundamental processes. They govern how substances change from one form to another. It is how stars forge elements. It is how life itself became possible on our small blue planet. Understanding them is like having a key to the universe. Chemical reactions are not just abstract ideas. They are not confined to laboratories with bubbling beakers. They are happening in the sun, producing light and heat. They are happening in the oceans, shaping our planet's climate. They are happening in the soil, allowing plants to grow. They are even happening as you read these words. Your brain is using chemical reactions to process information. Your body uses them to convert food into energy. It is a beautiful, intricate system. So, what exactly is a chemical reaction? In simple terms, it is a process. It is a process where substances, called reactants, are transformed. They change into different substances called products. This transformation involves the breaking of old chemical bonds. It also involves the forming of new chemical bonds between atoms. Think of it like Lego bricks. You can take apart a Lego car. You can then use the same bricks to build a Lego house. The bricks, atoms, are the same. Their arrangement is new. Every chemical reaction has its own cast of characters. We call the starting substances reactants. These are the molecules or atoms that will undergo a change. Think of them as the ingredients you gather before baking a cake. You have flour, sugar, eggs, and butter. These are your reactants. They exist in a certain state before the magic of baking begins. Each reactant has its own properties. It has its own unique way of behaving in the chemical world. Their destiny is to transform. Then we have the products. These are the new substances formed as a result of the chemical reaction. In our cake analogy, the finished cake is the product. It is very different from the individual ingredients. It has new properties, a new taste, and a new texture. Products are the outcome of atoms rearranging themselves. They form new bonds and new structures. The journey from reactant to product is the essence of a chemical reaction. It is a fundamental change in identity. The transformation process itself is like a carefully choreographed dance. Atoms in the reactant molecules must first break their existing bonds. This requires energy. Old connections must be undone before new ones can be made. Once bonds are broken, the atoms are free to rearrange. They then form new bonds, creating the product molecules. This bond-forming process usually releases energy. The overall change in energy determines if a reaction needs heat or gives off heat. It is a delicate balance of breaking and making. Consider a simple example: the rusting of iron. Iron, Fe, is a reactant. Oxygen, O2, from the air is also a reactant. Over time, these reactants interact. They undergo a chemical change. The product formed is iron oxide, Fe2O3, commonly known as rust. The strong, shiny iron transforms into a flaky, reddish-brown substance. This is a new material. It has properties entirely different from the original iron and oxygen. This is the power of chemical transformation. It is a constant in our universe. For a chemical reaction to begin, there's often a hurdle to overcome. This hurdle is called activation energy. Think of it like pushing a boulder up a small hill. Once you get it to the top, it can roll down the other side easily. That initial push, the effort to get it to the top, is the activation energy. Reactants need this initial input of energy. This energy helps to break their existing chemical bonds. Without it, they might just sit there, stable and unchanged. Activation energy is the minimum energy required to start a reaction. It's like striking a match. The friction provides the activation energy. This heat allows the chemicals on the match head to react with oxygen. Once the reaction starts, it often releases enough energy to sustain itself. Some reactions have very low activation energy. They can start almost spontaneously. Others require a significant energy boost. This could be in the form of heat, light, or even electricity. Imagine molecules as shy dancers who need a little encouragement to join the party. The activation energy is that encouragement. It gets them moving and interacting. It raises their energy levels. This makes them more likely to collide with enough force. It also makes them collide with the correct orientation. These effective collisions are necessary for bonds to break. They are necessary for new bonds to form. The higher the activation energy, the slower the reaction tends to be at a given temperature. This concept is vital in controlling chemical reactions. Sometimes we want reactions to happen quickly. We might add a catalyst. A catalyst is like a helper molecule. It lowers the activation energy. It makes it easier for the reaction to start. Think of it as finding a lower pass through the mountains. Enzymes in our body are biological catalysts. They speed up crucial life-sustaining reactions. Without them, these reactions would be too slow to support life. Activation energy is a gatekeeper of chemical change. One common type of chemical reaction is called a synthesis reaction. The word synthesis means to make something new by combining parts. In a synthesis reaction, two or more simple substances combine. They join together to form a more complex product. It's like taking individual Lego bricks, say a red one and a blue one. You then click them together to make a new, combined red-blue brick. The reactants are simpler. The product is more complex. This is the essence of building up. A general way to represent a synthesis reaction is A plus B yields AB. Here, A and B are the reactants. AB is the more complex product they form. For example, the element sodium, Na, is a soft, silvery metal. The element chlorine, Cl2, is a poisonous green gas. When these two reactive elements come together, they synthesize. They form sodium chloride, NaCl. This is common table salt, a completely different and essential compound. Two dangerous substances combine to make something we use every day. These reactions are fundamental to creating new materials. Think about the formation of water. Hydrogen gas, H2, can react with oxygen gas, O2. When they combine under the right conditions, they form water, H2O. Two gases combine to form a liquid essential for all known life. This is a powerful example of synthesis. Many industrial processes rely on synthesis reactions. They are used to produce plastics, fertilizers, and pharmaceuticals. They are the universe's way of building complexity from simplicity. Synthesis reactions are not just about simple elements combining. Sometimes, simpler compounds can also combine. They can form more complex compounds. For example, calcium oxide, CaO, also known as quicklime, can react with water, H2O. This synthesis reaction produces calcium hydroxide, KOH2, or slaked lime. This product is used in construction and agriculture. The universe is constantly engaged in synthesis. From the hearts of stars creating heavier elements to simple chemical mixing in a lab, it is about building up, creating something new and often more intricate. Section 5, Breaking Apart, the Story of Decomposition. Now let's explore the opposite of synthesis. This is called a decomposition reaction. Decompose means to break down into smaller parts. In a decomposition reaction, a single complex compound breaks down. It splits into two or more simpler substances. These substances can be elements or simpler compounds. It's like taking that combined red-blue Lego brick we made earlier. You then separate it back into the individual red brick and blue brick. The reactant is complex. The products are simpler. The general form for a decomposition reaction is AB breaks down into A and B. Here, AB is the complex reactant. A and B are the simpler products it breaks down into. A classic example is the decomposition of hydrogen peroxide, H2O2. You might have a bottle of this in your medicine cabinet. Over time, or when exposed to light or a catalyst, it slowly decomposes. It breaks down into water, H2O, and oxygen gas, O2. This is why hydrogen peroxide bottles are often dark. It helps to slow down this decomposition process. Decomposition reactions often require an input of energy to proceed. This energy can be in the form of heat, light, or electricity. For instance, heating mercury 2 oxide, HgO, a red powder, causes it to decompose. It breaks down into liquid mercury, Hg, and oxygen gas, O2. This was a famous experiment in the history of chemistry. It helped scientists understand the nature of oxygen. Electrolysis of water is another example. Electricity is used to decompose water into hydrogen gas and oxygen gas. These reactions are crucial in many natural and industrial processes. In nature, the decomposition of organic matter by bacteria and fungi is vital. It recycles nutrients back into the ecosystem. In industry, decomposition reactions are used to obtain elements from their compounds. For example, the production of metals like aluminum involves decomposing aluminum oxide. Understanding decomposition helps us break down complex substances. It helps us harness their simpler components for various uses. It is the universe's way of simplifying and recycling. Section 6. The Great Atomic Swap, Single Replacement Reactions. Let's move on to another fascinating type of chemical dance. This is called a single replacement reaction. It's also sometimes known as a single displacement reaction. Imagine a couple dancing and a new dancer cuts in. The new dancer takes the place of one of the original partners. In a single replacement reaction, one element replaces another element in a compound. One element is kicked out or displaced by another. It is a chemical swap meet at the atomic level. The general form of a single replacement reaction can be written as A plus BC yields AC plus B. In this scenario, element A is more reactive than element B. So, A swoops in and takes B's place with C. This leaves element B on its own. An example of this occurs when a piece of zinc metal is placed in a solution of copper 2 sulfate. Zinc is more reactive than copper, so zinc replaces the copper in copper 2 sulfate. The products are zinc sulfate and solid copper metal. You would see the blue copper sulfate solution fade. You would also see reddish-brown copper metal forming. These reactions are governed by something called the activity series of metals. This series ranks metals based on their reactivity. A more reactive metal can displace a less reactive metal from its compound. Think of it as a pecking order. The stronger, more assertive element gets to form the new bond. If the lone element is less reactive than the element in the compound, no reaction will occur. It's like the new dancer not being bold enough to cut in. The original pair continues their dance undisturbed. Single replacement reactions have practical applications. They are used in extracting some metals from their ores. For instance, iron can be used to displace copper from solutions of copper compounds. This is a method for recovering copper. These reactions also play a role in corrosion. For example, if a more reactive metal is in contact with a less reactive metal in a corrosive environment, the more reactive metal may corrode preferentially. This is the principle behind sacrificial anodes used to protect ships and pipelines. It is a constant competition among elements. Section 7. Trading places. Double replacement reactions explained. Now imagine two dancing couples on the floor. Suddenly, they decide to swap partners. Each dancer from one couple pairs up with a dancer from the other couple. This is similar to what happens in a double replacement reaction. It is also known as a double displacement or metathesis reaction. In this type of reaction, the positive ions and negative ions of two different ionic compounds switch places. They form two entirely new compounds. It is a more complex exchange than a single replacement. The general form for a double replacement reaction is AB plus CD yields AD plus CB. Here, A and C are typically positive ions. B and D are typically negative ions. The A ion from the first compound pairs up with the D ion from the second compound. Simultaneously, the C ion from the second compound pairs up with the B ion from the first compound. It's a complete partner swap. Two new compounds are born from this exchange. These reactions often occur in solutions. For a double replacement reaction to be considered to have occurred, one of three things usually happens. First, an insoluble solid called a precipitate might form. Imagine mixing two clear liquids and suddenly a cloudy solid appears. This is a precipitate. Second, a gas might be produced. You might see bubbles forming in the solution. Third, a molecular compound like water might be formed. These visible or detectable changes indicate that a new substance has indeed been created. Without such evidence, the ions might just be mixed. A common example is the reaction between silver nitrate solution and sodium chloride solution. Both are clear, colorless solutions. When mixed, the silver ion from silver nitrate combines with the chloride ion from sodium chloride. This forms silver chloride, which is an insoluble white solid precipitate. The other product, sodium nitrate, remains dissolved in the water. This type of reaction is used in many analytical tests. It helps to identify the presence of specific ions in a solution. It is a sophisticated atomic ballet. Section 8. Everyday alchemy reactions all around us. Chemical reactions are not just confined to laboratories. They are not just theories in textbooks. They are the silent, tireless workers of our everyday lives. They are happening constantly, all around us, and even within us. Consider the simple act of cooking food. When you bake a cake, heat causes a cascade of chemical reactions. Proteins in the eggs denature and coagulate. Starches in the flour gelatinize. Sugars caramelize, creating new flavors and colors. Baking powder or yeast produces gas, making the cake rise. It is truly kitchen chemistry. Think about a campfire or a gas stove. What you are witnessing is combustion. This is a rapid chemical reaction between a substance and an oxidant, usually oxygen. This reaction produces heat and light. When wood burns, cellulose and lignin in the wood react with oxygen. They produce carbon dioxide, water vapor, ash, and energy. Similarly, natural gas in your stove reacts with oxygen. It produces carbon dioxide and water, releasing energy to cook your meal. These are vital reactions for warmth and sustenance. Even processes we might take for granted, like the rusting of an iron gate, are chemical reactions. Iron reacts with oxygen and water in the environment. This forms iron oxide, or rust. This is a slow oxidation process. It gradually changes the properties of the iron, making it brittle. On the brighter side, photosynthesis in plants is a life-giving chemical reaction. Plants use sunlight, water, and carbon dioxide. They convert these into glucose and oxygen. This oxygen is what we breathe. We are all connected through these reactions. Cleaning with soap or detergent also involves chemical reactions. Soap molecules have a special structure. One end is attracted to water, and the other end is attracted to oil and grease. This allows soap to break up grease into smaller droplets. These droplets can then be washed away with water. Even simple acts like dissolving sugar in tea involve physical changes. But many biological processes in our body, like digestion, are a series of complex chemical reactions. Our bodies are intricate chemical factories. Life is a symphony of reactions. Section 9. Chemical reactions, engines of our world and beyond. As we journey through this cosmic exploration, one truth becomes clear. Chemical reactions are fundamental. They are the engines that drive change in our world. They are essential for life as we know it. In medicine, understanding chemical reactions allows us to develop new drugs. Drugs work by interacting with molecules in our body. They trigger specific chemical responses to fight disease or alleviate symptoms. Pharmacists and doctors rely on this chemical knowledge daily. It is a powerful tool for health. In industry, chemical reactions are the backbone of manufacturing. They are used to produce everything from plastics and fertilizers to fuels and building materials. Chemical engineers design and optimize these reactions. They make processes more efficient and sustainable. They also work to reduce harmful byproducts. The clothes we wear, the cars we drive, the technology we use, all are products of carefully controlled chemical reactions. Our modern society is built upon them. They shape our material existence. Environmental science also heavily relies on understanding chemical reactions. The study of pollution, climate change, and remediation strategies all involve chemistry. For example, acid rain is formed by chemical reactions in the atmosphere. Pollutants like sulfur dioxide and nitrogen oxides react with water and oxygen. Understanding these reactions helps us find ways to reduce their impact. Similarly, developing green technologies and renewable energy sources often involves innovative chemical processes. Protecting our planet requires chemical wisdom. In conclusion, chemical reactions are not just abstract concepts. They are the dynamic processes that shape our universe. They occur from the smallest scale of atoms bonding to the grand scale of stars forming. They are in every breath we take, every meal we eat, and every product we use. Understanding them empowers us. It allows us to create, to heal, to innovate, and to protect our world. The study of chemical reactions is a continuous journey of discovery. It reveals the intricate and beautiful chemistry that makes everything possible. The cosmos is indeed alive with chemistry.